Hierarchical hybrid memory management and OS for tiered memory systems. Modern computer systems are facing numerous new challenges, such as fast growing memory footprint, rapidly increasing energy consumption, high demand for throughput, etc. In a typical cloud computing environment, it is critical to have a large capacity memory system that can provide fast data retrieval and operate at a low energy cost. Recently, the emerging non-volatile memory (NVM) technologies bring an opportunity to build such hybrid memory systems, 1, 3, 10, 11, 12. However, efficiently managing such hybrid memory systems requires considerations of a variety of factors, including the distinct memory characteristics, diverse workload behaviors, and architecture features, which poses new challenges for the memory management mechanism in modern operating system. OS 2, 4, 5, 9, 13, 14, 15, 16, 17, full hierarchy hybrid memory management. For the first time, MEMOS achieves a full hierarchy, application demand driven memory management covering cache, channels, and DRAM/NVM banks. Dynamic memory bank, channel rebalancing. We propose a memory bank rebalancing approach to provide higher bank parallelism and boost data transfer. Open source Sysmon. We open sourced Sysmon, a kernel tool used to collect memory footprint, page hotness, reuse patterns, etc. Real implementation. We implement MEMOS in Linux. Kernel 2.6.32.15. Channel allocation. Channel resource in MEMOS is primarily used as a way to designate different types of memory resources, and is scheduled based on an application page's preference for DRAM or NVM. As such, our scheme attempts to direct hot pages into DRAM channel, especially for those with WD features. Load-intensive pages can be directed through NVM channel onto NVM without hurting performance. Cold pages are kept in NVM to save energy and reserve DRAM capacity for hot and WD pages. Cache allocation process. In our system, LLC resource is partitioned into dedicated slices to serve the memory requests directed onto DRAM and NVM channel respectively. As memory-intensive pages with thrashing behaviors are mapped into DRAM for performance, isolating them in LLC can help to avoid thrashing other data, such as the data from NVM channel. Bank partitioning and balancing effective in NVM due to its longer latency raised by memory interferences on bank among threads and hotspots. Even for DRAM, a balanced bank parallelism can hide memory latency and is crucial to achieve desirable full hierarchy management for hybrid memory. By combining all of the above, we construct a full hierarchy memory management strategy that manages resources from the upper levels, that is, cache, through the middle levels, that is, channels, to the lower levels of the memory banks. Deployment of MCHA. We emulate MCHA in Fig.3 by deploying a channel partitioning mechanism, 7, to divide the memory address space into two segments, on a typical multi-core server with Intel i7 series CPU and dual channel with 8 GB DDR3 main memory, that is, energy and latency. Migration mechanism. Fig.4 highlights MEMOS' migration mechanism. In summary, MEMOS tries to segregate hot pages with WD label to DRAM, and keep road pages as well as cold pages in NVM, avoiding bank conflicts for efficient data migration. In our mechanism, the bank-level utilization information is always monitored, and such information is used by page placement routine in MEMOS to avoid banks with hotspots. Energy, latency and lifetime. We evaluate the energy savings and memory latency reduction using the emulation system in Fig.3. For MCF, the dynamic energy in NVM channel is significantly reduced from 2.13 MW to 0.001 mW. Rebalancing and caching effects. Mentioned before, Memos rebalances hot pages across memory banks for NVMe and DRAM channel by combining both of the rebalancing hot pages across banks for a specific application and partitioning memory resource across different threads. In single-thread cases, significantly reduced by around 60–70%, indicating that the bank parallelism is significantly improved. Overall performance of Memos on MCHA. We compare Memos on MCHA with some typical resource scheduling approaches, that is cache bank vertical management. 8,9, and utility-based cache partitioning without channel partitioning on our platform. Fig.7 illustrates the experimental results. 5. Memos with MCHA achieves an average of 19.1% performance gain, and outperforms the state-of-the-art approach by 7.3%, up to 11%. Moreover, Memos improves GOES, indicated by max slowdown, 6,8,11, significantly, 23.6% on average. Take the case in point 11 as an example, Memos on MCHA. Example, Memos on MCHA can bring 34.1% benefits for GOES, while the utility-based cache and vertical cache bank partitioning with dual-channel interleaving scheme improve GOES by 13.2%, 19.4%. Our new mechanism exhibits obvious advantages, and outperforms them by 20.9% and 14.7%, respectively. Because the full hierarchy mechanism reduces memory interferences at each level of the memory hierarchy, outperforming the vertical cache bank and other single-level cache optimizations.